My name is Vineet, and I'm a student of BSc Final Year Chemistry Honors. Today I'm presenting my topic on my presentation is basically on the topic on Killiani-Fisher synthesis first, and then on rough degradation, and then on whole degradation, and then on structural elucidation, and I'll briefly describe all these methods in just few minutes. So number one, Killiani-Fisher synthesis. Killiani-Fisher synthesis is basically done to convert an aldopentose into aldohexose. For example, if we take an aldopentose that is D-rhabinose, then we have to convert it into D-aldohexose by successive steps in which we will get a mixture of basically mixture of diastereomeric mixture and diastereomeric pair in which we will get, if we use glucose then we will get glucose plus mannose, and if any other aldopentose then we will get another mixture. So first we will treat our aldopentose that is D-rhabinose with HCl, and it will convert into a cyanohydrin. This cyanohydrin, when we heat this when we hydrolyze the cyanohydrin in the presence of acid, that is acidic hydrolysis, then it will convert into carboxyl group. So carboxyl group remain attached under C double when C double bond OH group attached at carbon number 1. Now if this is heated, there are two mixtures. First is of glucose and the other is of mannose. So if this is heated, it will convert into a lactone. So glucose will convert into gluconolactone and mannose will convert into mannolactone. So if this is heated, then lactone formation starts. And if this is treated further with sodium amalgam, that is sodium and mercury in the presence of acid, then at pH 4 to 5, then it will basically reduce and it will convert into our endohexose. That is glucose will convert into arabinose will convert into a diastereomeric mixture of glucose and mannose. So this was my Killiani-Fisher synthesis. Now we'll come on to the process, that is a degradation process. That is, first is rough degradation and the other is whole degradation. In rough degradation, first we will take endohexose, that is glucose, for example, we are taking. So when we convert this glucose into an aldopentose, because we have to degrade, so we have to subtract one carbon from the chain. So first we will treat it with bromine water and the gluconic acid forms. Now this bromine water is gluconic acid is formed. Now this gluconic acid is treated further with calcium carbonate, so that salt formation occurs. Now calcium gluconate forms, and further heating it to high temperature, it will give the corresponding aldopentose, that is D-arabinose. Now we will come on to our second type of degradation, that is whole degradation. Now in whole degradation, first we will convert our aldopentose into oxime by treating with hydroxylamine. Now further, when we treat with this hydroxylamine, that is oxime with acetic anhydride, then C double bond NOH group get dehydrolyzed to, and water is basically removed off, and it will dehydrolyze to cyanide, yani nitrile groups, and the 5OH groups are acetylated, and a cyanoacetylation occurs in the cyanoacetylated compound forms. Now if this cyanoacetylated compound is further treated with the tolerance reagent, that is AgNO3 and an ammonium hydroxide solution, then our aldopentose, that is D-arabinose, is formed. So finally, we will come on to our structural elucidation part. We are concluding the structure of glucose and fructose. So first of all, in glucose, we have to confirm that if it contains if it contains an carbonyl group or not. So for that, we will treat with HCl, or we will treat with hydroxylamine, or when we treat with the phenylhydrazine. Then if this glucose contains carbonyl group and then corresponding oximes are formed with hydroxylamine treatment, and with the HCN, it will form cyanohydrin, with phenylhydrazine it form phenylhydrazone. So this confirms the presence of a carbonyl group in glucose. So again, if carbonyl group. So which type of carbonyl group it will it is present in it? It is confirmed further by treatment it with bromine water. So when we treat it with bromine water, it converts it gives a monocarboxylic acid, that is gluconic acid, containing the same number of carbon atoms, that is of glucose. Now if this monocarboxylic acid has 5 carbons and 6 carbons, and glucose is also 6 carbons. Now this once C double bond OH group comes obviously from the CHO group, so it confirms that the presence of aldehyde. So this confirms the presence of an aldehydic group in the glucose. Now for the confirmation that glucose has which type of alcoholic group, that is to find the nature of alcoholic group. First we will treat it with the HNO3, concentrated HNO3. It will give the glucaric acid, dicarboxylic acid, from which we will determine that one hydroxyl group is primary in nature and the other four hydroxyl groups are secondary in nature. And before it, we have to find out that how many types of how many hydroxyl groups are present. So there are five hydroxyl groups. This confirms from the treatment when we treat it with the acetic anhydride in pentacetate forms. It confirms the presence of five hydroxyl groups. So so again we come on the dicarboxylic acid, saccharic acid. So in saccharic acid, there are two C-double bond OH. One is from aldehyde group and another is from primary alcoholic groups. So it confirms that four OH are secondary and one OH is primary. Now again, finally comes out to the last part, that is on in which in this glucose how many carbons are present and in the arrangement of these carbons are what. So for that we will treat it with hydroiodic acid in the presence of red phosphorus and heating it to the 473 Kelvin. So it gives a straight chain of N-hexane and plus 2 iodohexane that confirms the presence that in glucose 6 carbon atoms are arranged in a straight chain.